Hello everyone, this is Akshay here and welcome to my channel. So, if you are new to this channel, please like, share, and subscribe so that you can learn, maintain, and grow our streak together. So, let us see what the today's question is about. It is about the name of the question is Best Node, the medium category question, and let us see what this question says, and we'll think of the different approaches if possible, and then we'll code it, right? So, you are given a tree rooted at node 1. The tree is given in the form of an array P where PI denotes the parent of the node. So first of all, yeah, if you have read this question, then I hope that you may be getting difficulty in building the tree, right? In the difficulty in the sense you may have thought that it is a lengthy process to build a tree at first and then to visualize that how the things are going. So that's not a problem. I face that difficulty as well. So let us see now. So there is an array pi which denotes the parent of the node root parent of the node I. If p also the first node p1 is equals to -1 as 1 is the root of the node, right? Okay. So every node I has the value ai associated with it. So study these two statements. The pi has the parent of root node I. The ai has the value of the node associated with I, right? Now what you have to do is written in these lines that at first you have to choose any node to start with. After that, from a node which you have chosen, you can go to any of its child nodes, right? So you have to keep moving to a child node until unless you reach a leaf node. So every time you go to a new node, you write its value. Let us assume that integer sequence in the path b, and whenever you visit a child node, the first node to second node, you have to do b1 minus b2. When you visit the third node, you have to take the plus value of the particular node, then the minus and plus until and unless you reach the leaf node. Now in this particular traversal, you have to find the maximum value of this function of b, right? So let us suppose, first let us see that how these two integers and n are helping us to build the tree. Then we will think of the approaches, right? First let us do the input and output dry run, then we will think of the approaches because that's the first thing we always do, right? So let me explain you this way that a has the value, right? So let me write this thing as we have three nodes. So let me write it as n1, n2, and n3. Now let me write the A array above it and the P array just below it. So A array is saying that the value of n1 is 1, the value of n2 is 2, and the value of n3 is 3. Right? Now the P value is -1, 1, and 1. So this is implying that this is the root node. This is the root node. Right? So n1 is the root node, right? So let us make a root node with the value 1 because it was written in the place of n1. This is the thing here. This is the index of n1, n2, and n3, right? So okay. Now what this is saying, what the question was saying, that pi is parent of I. It was saying this, right? So what can I infer from this point is that n1 is parent of n2. Similarly, from this line, I can say that n1, the pi is 1, right? So I'm saying the n1 is parent of n3. This is the ith, right? This is the ith index starting from 1, right? Okay. So I have inferred these two things. Now let us draw the tree. Let us draw the tree. So the root node we decided, we know that it is 1, right? Now what is the thing that n1, this is my n1, right? This is my n1. So n1 is parent of n3. So where is n3? So n3 is there. N3 is there is one node, let's say. There is one node n3 which has the value as 3 here, as you can see. So I will say 3, right? Similarly, from this you can say n1 is parent of n2. So there will be another node named as n2 and n2 has the value of 2. So I will say like this. So this is my tree now, as you can see, right? That 1, 2, and 3 and n1, n2, and 3 values are given, right? I guess we are on the right track. Okay. Similarly, I have written for the second test case as well. Let us draw the tree and then we will see. So n1, the pi is -1, right? The question says if it is -1, then that is a root node. So n1 is the root node which has the value as 3. So let us make a node, root node, this 3. And this is nothing but a n1, right? Now the what the second line is says, the n1 is the parent of n2, right? So let us make it. So n2. So n2 is here, right? And its value is 1. Okay, right? Now n2 is parent of n3, right? So let us make another. This n2 is parent of n3 and n3 has the value of 2. So as you can see, this is our tree, right? Which has the value of 3, 1 and 2, which has the value of 3, 1 and 2. The one which are not written in the parenthesis is representing n1, are representing node 1, is representing node 2 and it is representing node 3. And the in the parenthesis the values are given, that is the A array is given there, right? Okay, so let us get back to the question and collect the constraint. So what was the constraint given? Constraint in the sense what was said in the question, that you can visit any node, right? And you have to stop at leaf node. You have to stop at leaf node, right? And while traversing, you can visit children, right? Visit any node, and in the traversal, you have to go to its child. And as soon as you reach the leaf node, you have to stop it, right? And the traversal is like this. So let's say in any node you have chosen B1, and the children of this node will be, let's say, two node, right? Let's say x and y. So since you have taken this direction of y, then you will say x minus y. Then y, let's say, have children z and let's say L, right? And suppose from Y you visited Z, so you will say plus Z, right? Similarly, you will keep on going until you encounter a ln leaf node, right? So this will be your first path, right? But you can also you would have also gone into this way, that you went to B1, then you went to Y, then you went to L, and then you encountered leaf node. Similarly, you can take in the path of B1 to X as well, right? So that means from each and every node you have to consider all the possibilities. So what's the logic then? DFS, DFS, that for each and every node you have to call a DFS function, you have to pass the root node, right? Then in the base conditions you have to write that if it reaches the leaf node or not, right? So you can say that if root dot left and root dot right, if both are equals to null, right, that means that you have returned your leaf node, right? And you will say return, right? Similarly, you have to first take minus sign then plus sign. So for that you can maintain a global variable, let's say flag equals to 1. So for the first time when you visit, you will say that if flag is equals to 1, then take the plus sign, right? Take the plus sign in the sense how you can write that. You can write it as, let's say you are storing this thing in answer. So answer plus equals to root dot data, right? Plus answer plus equals to root dot data, and then you change this flag to 0. Similarly, you will write another if case, that if flag is equals to 0, then you choose the minus path. So answer minus equals to root dot data, right? And then you change the flag again to 1. So this will be your two ifs, right? And at last you will check again that if uh, if left node exists, I am writing this as at left node exists, then call DFS for left node as well, that call DFS for left node. And if right node exists, I am writing it as RGHT net node exists, then call the DFS for the right node as well, right? And this recursive function will give you the answer of the maximum possible traversal path, right? But what would be the time complexity of this code? For each and every node, you are traversing the the for each and every node you are visiting all the particular nodes, right? You can say that. So suppose, let us imagine with a tree. So let's say this is our tree. Let's make a big tree now, so that we can visualize the time complexity of this code. So it will be O, O, O and O, right? So for each and every node, you are traversing till the root node, right? So the worst case will be that you are starting from the root node, and then you are taking, let me draw this. You are taking this path, then you are taking this path, then you are taking this path, and then you're taking this path and this path, right? Similarly, for each and every node, you read the leaf node. And since you're not maintaining any visited array as well, right? So the if you have taken another tree as well as the skewed tree, right? So the amortized complexity, it may look like you as the n square, right? But it's not the case. The amortized complexity can be said as O of n, right? Yes, and similarly, the space complexity will be what? The depth of the tree. Suppose there is a skewed tree, then you have to make the recursive call store in your tree so that you can once this reach the leaf node, then you can return and check for the left right possibility if there exists something or not, right? So the space complexity will be again O of depth of tree, right? Okay, okay. So if you are able to code this approach as well, right? So your code will be submitted, right? but uh, but it would be a like very complex code if I say that you have to call the recursive function each and every time. And let me analyze the time complexity again, because I'm also solving the question for the first time. So let me think that it will really be n or not. I think it will not be n. You guys are right if you are thinking. In the DFS, in the graph, when we do the DFS, we always maintain a visited array, if you remember, right? And when you maintain a visited array, that it gives you an assurance that you are not visiting the element twice, right? But here the assurance is not there. For each and every n, we are visiting each and every node, maybe each and every node, to reach the leaf node, right? Right. So in that case, I can say that the maximum complexity will be O of n into the depth of the tree, right? The depth of the tree. Yeah, I'm right. So let us assume, so it will, let's say there's a skewed tree, right? So it will be O and O. So for this n, I have to visit n times again. So it will be n square. Yes. So it will be n square and this code will not work. So maybe you have to do some optimization regarding DP or memorization, a tabulation or memorization, store the recursive for problems and you can do it, right? So try to code this approach. We have discussed multiple times in our DFG POTD history that I first show you the recursive approach, then I show you the memorization as well as the tabulation. But this time I am handling this case to you guys, right? Because I have to discuss one optimization as well. So try to put this thing in the recursive approach, then try to you see the TLE, then try to do in the memorization and then the tabulation, and comment down in this video that the yes, uh, maybe done the recursion, done the recursion, right? Let's write nail the recursion, right? So comment down this sentence if you're able to code this approach as well, and if not, if what were the challenges that you faced, right? So we can discuss over it more. So I hope I have given you enough intuition on this, right? And let us proceed ahead with the another approach now. Maybe some optimizations are there, right? So since the constraint part is given as n equals to 10 power what 5, then obviously we cannot code this approach in n square, right? Or let's say you cannot code this approach in exponential time complexity as well, not in n square as well. You need to go below the n square. So 10 power 5, I believe it is n root n, the worst complexity. You can watch my time complexity video to visualize that how I'm saying n root n. And then you can go below n root n as n log n, then you can take n and everything which is below n root n, right? So what can we think of? So what I'm saying is that why don't we do the reversal thing? Now what are we doing that for each and every node we are considering the two possibilities going left and going right, and for each then you are going left and going right and then maintaining the maximum sum, right? Why not do this thing that we know we have this tree 0 1 1 2 and 3, right? And we know that we need to reach the leaf node because that's our stopping point. So let us start from the leaf node itself, right? And what will be the benefits, guys, that when we start from the leaf node, when we start from leaf node, then we know in what direction or in what node I have to visit next. In what node I have to visit next. Because one array is given us as P of P array, right? So I know the parent of 3 will be 1. I can infer from that, as well as there is one array of this thing as which is have the associated value, right, with that particular node. So I can use these two array to exploit this technique, right? So how can we find that how many leaf nodes are there, right? So what uh, in the question is given is the parent nodes are given, that is -1, that's belonging to the root node, 1 and 1, right? And if you make this tree, it will say that the tree is nothing but looks like 1, 2 and 3. Similarly, for this array, you can see the parent is given as -1, 1 and 2. And if you draw this tree, you will get 3, 1 and 2, right? You can see that the integers that are not present in this parent array are the leaf node in my tree, right? Can you see that? Can you see that? So if I say, because in this parent, what it is saying, that you have the parent of this node, that 1 is the parent of node 2, 2 is the parent of node 3. So if some node is not present in the parent array, that means that particular node is not the parent of any another node. And definition of leaf node itself is that it is not the parent of any such nodes. All childrens are null, right? So what can I do is I can maintain a set, right? And I push all these which are present in my parent, that is in this set I will have -1, 1 and 1. Now I will iterate for number of nodes I have, right? So I have number of nodes as 3, right? So I will check for 1, 2 and 3. Let's say for I equals to 1 to I less than equals to n, right? And I will say that if 1 is present in this set, that means it is not a leaf node, so I will say it is a non-leaf node. If 2 is present, so I can see that in the set it is not present, right? And this set is nothing but the pi entries, so I will say that is my leaf node, right? And then the 3 is in my leaf node, right? So I can doing these two things, doing these two steps 1 and step 2, I can infer that what are my leaf nodes, right? Then what can I do next to say that how should we tackle our according to the leaf nodes, how should we travel in the upright direction, in the upward direction, right? So let's see that. Okay, so following those two previous steps, I have the leaf nodes in my hand in my list, let's say 2 and 3, right? So let me give you a pseudocode now. So what is my requirement? That from 3 I will move to 1, right? That is what I need to do, that I from 3 I move to 1, and when I move to 1 I need to convert this 3 into -3, and then when I move to 1 it should be -3 plus 1, that is -2. And whenever I am moving to each stage, I need to consider the max value, right? Because I need in the traversal what is the maximum value, and I can start from any node, right? So I will maintain the maximum value. I will say that in this, when I started from this leaf node, my maximum value is 3. When I move to the direction which has given to me in via this array, via this tree edge, then I can see that I can move to 1, right? Because you have the privilege to move only to child, right? So I'm just doing the reversal thing, moving from leaf to its parent. That's the same thing, right? So -3 plus 1, it will be +2. So the max will still remains 3, right? Now the next leaf node is we are having 2. The max is above is pointing to 3. The current sum, let me maintain a sum variable as well. So sum is 3 here, sum is 2 here. So the maximum sum will be 2 here, and sum I will reset it. For each and every node I will reset the sum to 0, right? So sum, the maximum will be 3 again, sum will be 2. Now 2, when I move to my another node, I need to change the sign, right? So I will change the sign -2 plus 1. So my sum will point to -1, but the maximum will still be pointing to 3, right? Right? So what can I write this pseudo code for this thing? That first, before launching this while loop, right? I had to make a sum which will be pointing to 0, right? And yes, so for each and every leaf, for each leaf, this thing will run. For each leaf, we will check that why the leaf not reaches the root, right? So we have to do something. So what are the things? So first I will change the sign, then I will write changing the sign with sum star -1, it will do the trick, right? Then include the current value, that sum plus equals to, right? And let's store this leaf into a variable as current node, right? And since the current node is a 1 based indexing, right? So what can I say is the, I'm writing cn. Cn minus 1, I can use minus 1, right? Similarly, for each and every traversal step I took, I have to maintain an answer variable that will have this thing, the maximum. So math dot max answer comma sum, right? And at last, I just have to update my current node pointer to the parent of the node which I processed now, right? So what I will say, the current node will be nothing but the parent of current node minus one because it's a one based indexing. Let me dry run this code for you, the exact code for you, so that we can have a clear understanding, right? Okay, okay. So let us write the array here and then we will see for ourselves. So the tree was 1, 2 and 3, right? So bear with me for maybe 5 to 6 more minutes and we will see. So let's say the AI was A1, 1, 2, 3. The PI was minus 1, 1 or 1 and 1. So let us do it again for second test case because I already showed you for the first one, right? So let us do the exact dry run for the second test case. So the tree was looking as 3, 2 and 1, right? Which it was pointing as n1, this was n2 and this was n3 if I'm not wrong. Yeah, it was like this. Okay, so the array distribution was like this. How was the array distribution? Let me look at my uh, the problem. Okay, so I have written the array and the parent here. So my current node, the leaf here itself is only the node 3, right? So I will have this in my list of let's say in the list of leaf node, let's say leaf list. So I will pick out this element, so it will 3, right? It will say 3. So my current node is pointing to 3. So what I will say that I need to mention the associated node value of this. So what I will say that sum plus is equals to a of 3 minus 1 because since it's a zero based indexing, and as you can see the 3 minus 1, that is the tree was actually 3, 1 and 2, right? So if you see 3 minus 1 is nothing but a of 2 and a of 2 is pointing to which one? This 2, right? And as you can see that the n3 value is actually 2. So we can actually use this a array and the p array to use this pre-processing. So I can say that initially sum was equals to 0 when we start from each and every leaf node. So it will be 0 plus 2, that is 2, right? When we come now, the current node will be updated to parent of 3 minus 1. So that is parent of 3 minus 1, that is 2. So it will be updated to n2, right? And as you can see from the graph itself, from the tree itself, that the parent of n3 was node 2, right? Okay, let us do the second iteration. So my current node is now n2, right? Right? And I have to change the sum. I have to change my what the alteration. I have to change the sign of my sum. So initially, the previously it was 2, right? And for each and every iteration, I have to maintain max also. So let me maintain the max with the green color. So the maximum here it will be 2, right? Now the sum has changed to minus 2. Let me show the next iteration with the different color. So it will be minus 2 plus the a of the current node was pointing to 2, so I will take the value of 2 minus 1. So it will be minus 2 plus a of 2 minus 1, it is 1. And as you can see that the node 2 was actually having the value 1, right? So we are on the good page. So it will be minus 2 plus 1, that will be minus 1, right? Now the current node will change to parent of 2 minus 1. That is, parent of 2 minus 1 is nothing but n1, right? n1. And as you can see that the parent of n2 is actually n1 in the tree we build. So now my current node is n1 and the maximum value previously it was 2 and it's now updated to minus 1. So again it will be 2 only, right? Now the current node is n1 and how my sum will behave. That sum will be again change its sign. That will be minus of minus 1 it will be doing and it will do plus of the current node which I am at. So I am at 1. So I will do 1 minus 1. So it has the value of 3. So it will be 1 plus 3, that is 4, right? Bear with me for some more minutes and you will be definitely getting this logic. So this is 4, right? And now my current node is what? P of what? 1 minus 1. So P of 0 is nothing but minus 1. So we have reached our root node. We have processed our root node, right? And we can stop our while loop now. and you can see that the max now is the current node sum is pointing at 4, and I can update my max with 4. And if you tally also from the given output, you will see that the 4 is the answer. So now I think we have a much clearer understanding that how the code is behaving, and we can just replace this while leaf node reaches the root with what? While we are updating the current node, right? So I will say while current node is not equals to -1 to these 4 steps, right? So I explained you all the processing. I've explained you these first 2 steps as well, that we need to maintain a set. We are maintaining a set just to so that we can pick out our leaf nodes, in O of 1, right? O of 1 operation. Okay, so let us start coding this section now, and we will resume the video. So you also try to code this first and second step, and I will also do at the same time, and let us resume the video now. Video. Okay, so I have written the first and second step. So I have maintained a set, as we talked about, as we discussed, that it will have the non-leaf nodes. The non-leaf nodes, we can get it from the p array, because it has all the parent nodes, right, of some other node. So that means it cannot be a leaf node, right? So that means it is a non-leaf. So that's why I made a non-leaf, added all those nodes. Then I have made a list of leaf node. So whatever the index which is not present in my p array are all part of the leaf node, right? So that's what I have done. Iterated from 1 to less than n equals to n, because started the node starts from 1 to n, right? Less than to actual equals to n. So if that particular index is not present in my set, then I have added those nodes as leaf node in my list, right? Now the step 3 is that we have to traverse from leaf to root and store the max at each and every time we visited a new node, right? What were the advantages of doing this? Then since we know in which direction we have to move, since the parent is already defined there, so this operation will be O of 1, right? We can move to each and every step in O of 1, and we do not have to make any track of recursive calls and come back to visit the another child, right? I hope you are able to relate to this point as well. I explained you in the brute force technique, right? So let us do this thing. So I will say for int so let us iterate in my list. So I will say for int leaf in the leaf nodes, in the list of leaf node, right? Let us save this leaf into a node current pointer, right? So I will say int current node is leaf, right? And let us start now do the processing. The first step was to maintain a sum variable, right? That is equals to 0. Now there is one loop till when our current node goes beyond the processing of our root node. So we have to do the processing until it reaches the root node, right? So if I mention the command for you guys, let me do that. Okay, so this is the while loop while our current node reaches the root, and it will process that thing as well. And since the function b, as you can see here, it is the plus minus again for each and every next time we visit it. So let us do this thing, that sum is equals to nothing but minus of sum, right? And then I will say that plus equals to sum plus equals to a of current node minus 1. We can take the associated value of the node using the minus 1 using the 0 based indexing now, right? Similarly, update the answer as math.max. Let me write the last 2 lines, the same thing which I have explained you in the pseudocode, that is update the max and the update the parent pointer. So let us do. So I mentioned the last 2 steps, the exact we dry run in the paint section, and at the last we just have to return the answer, right? The maximum passable value for each and every traversal for each and every time we visited a new node. So let us compile and run, and we will see. So the expected and our output matches. So let us hit the submit button, and before hitting the submit button, okay, so I have hit it. So let us see. Uh, Okay, so all the test cases passed successfully. So let us discuss the time complexity again for this approach as well. So what I'm doing is that we have our tree 1, 2, and 3. So I am doing from leaf node to the top and then from the leaf node to the top. And in the meanwhile, whenever I am visiting and each and every node in between, I am maintaining the max variable. So what I'm doing is for every leaf node, I'm doing this thing. For every leaf node, I'm doing this thing, right? And the leaf node will be much lesser than the non-leaf node will be much lesser than the non-leaf node. I'm not talking about the small cases, but I'm talking about the larger cases. Like let's say the tree have this structure, the skew tree. In the skew tree, it will just take O of n time, right? Because there is one only leaf node, I will traverse to the top, right? And for traversing to each and every node, it take O of one time using the P and Ath array. But let's say if we have some complex trees where the multiple root non-leaf and multiple leaf nodes are there, but still, if you see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in the 12 nodes, there are only 3 leaf nodes, right? So it will be as good to say that we are doing k of n times traversal. K is the leaf nodes and we are traversing the whole tree, let's say, right? Or not the length tree, let the depth of the tree, depth of tree. So in this case, you can say that the amortized complexity will be that you are traversing the maximum of O of n times. So you are traversing each and every node, right? Because this constant can be ignored, right? And in the case of skewed tree, the depth of the tree will be n. So that is our worst case, right? So that's why we can say that the amortized will be O of n, right? Similarly, for the space complexity, are we maintaining something? We are maintaining a leaf node list as well as a set, right? So it will be directly we are pushing all the pth elements, so it will be O of n. So the space complexity will be also O of n and the time complexity will also be O of n, and that is the reason this code got submitted, because it's a 10 power 5 complexity, much less than 10 power 8. So definitely it will get submitted. So I hope you were able to get the all three approaches I explained to you, although I have not mentioned you the code of the first two approaches because we have done it several times, right? So I highly recommend you guys, before moving to the optimized approach, try this DFS approach and optimize it using memorization if you can do so, and comment down in the section that yes, you have nailed the recursion and the DP, and if not, I will definitely help you to this to code this approach as well, right? Because it's already 30 minutes, you can see, because the second optimization was a bit longer to explain. Now the last thing that I need to tell you guys is that this is the Java code in the right hand side, and that's the C++ code. So the language should not be a barrier for any learners here. So you can use this code as well for the C++ user, right? So there's just the difference in the syntactical, all the logic remains same. Like the long becomes the long in C++, hash set becomes unordered set, and RLS become vector and all, right? So if you're coding C++, you must be definitely getting this logic, this syntax, not logic. So that is it for today. So that's the end of day 134. Let us meet again tomorrow for day 135. And I'm telling you again, do not skip that DFS approach. Try to code it yourself. I've given you enough intuition. And let us meet tomorrow, yeah. So it was so hectic. Till then, bye bye. Keep learning, keep growing, and take care.